Hello there, and welcome to Sleep Science Chronicles. Tonight, we're going somewhere vast and quiet. We're going to drift through the lives of galaxies, not as observers reading from a distance, but as explorers moving through them, wandering their structures, passing through their arms and halos and hidden spaces the way you might wander through an enormous building you've never been inside before. Imagine for a moment that you could shrink the universe down to something you could walk through. That galaxies were rooms, and the space between them was a long, dim corridor. Tonight, we're stepping inside. We're going to move slowly, notice what's around us, and let each discovery settle before we move on to the next. Some of what we find will be familiar: the glow of stars, the sweep of spiral arms, but much of it will be hidden. Quiet processes unfolding over billions of years, invisible structures holding everything in place, rivers of gas you cannot see, flowing through spaces you didn't know existed. The deeper we go, the stranger and more beautiful it becomes. You don't need to remember any of it. You don't need to take notes or stay alert. Just come along. Let your breathing slow. Let the day fall behind you. We'll do the exploring together. And if you drift off somewhere along the way, that's perfectly fine. The galaxies will still be here in the morning. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing. It helps others find their way here too, one sleepy soul at a time. But for now, settle in. Let's begin. Let's start with the simplest question. What exactly are we stepping into when we enter a galaxy? The word itself comes from the Greek galaxias, meaning milky, a reference to that pale band of light stretching across the night sky, which is our own galaxy seen from the inside. For most of human history, nobody knew what that band was. It took telescopes and centuries of patient thinking before anyone realized it was a structure, an island of matter, vast beyond imagining, and just one among hundreds of billions scattered across the universe. A typical large galaxy contains somewhere between 100 billion and 400 billion stars. That number is hard to feel. If you tried counting one star per second without stopping, it would take you more than 3,000 years to reach 100 billion. And those stars are only the visible part of what's here. For every kilogram of starlight, there are several kilograms of gas and dust drifting in the spaces between stars, and perhaps 5 to 10 times more mass again in the form of dark matter. Invisible, untouchable, and yet holding everything together with its gravity. So as we step inside a galaxy, most of what surrounds us is something we cannot see. Let's look around. The first thing you'd notice, if you could somehow see the galaxy from the outside, is its shape. And the shape tells you a lot about where you are in the galaxy's story. The most visually striking are the spiral galaxies, flat, rotating disks with luminous arms curling outward from a bright central bulge. About 60% of all large galaxies in the nearby universe are spirals, including our own Milky Way. Their arms glow with the blue-white light of young, hot stars, and their disks are rich with the gas and dust needed to form new ones. Step inside a spiral galaxy, and you're inside something that's still actively making stars. It's still breathing. Elliptical galaxies feel very different. Imagine stepping from a busy, luminous workshop into a vast, quiet hall. Ellipticals are smooth, rounded, and reddish in color. There's very little structure inside. No arms, no dramatic lanes of dust, no bright knots of new star formation. These galaxies are filled with old stars, and the gas that once fueled creation is mostly gone. They've entered a kind of retirement. Not dead, the stars still burn, still orbit, but no longer building anything new. Some of them are enormous, containing several trillion stars. They are the largest galaxies in the known universe, and also the quietest. Between these two types, there's a whole spectrum of forms. Lenticular galaxies have the disk shape of a spiral, but have lost most of their gas. Galaxies caught mid-transition, like a workshop that's been cleared out, but not yet repurposed. Irregular galaxies have no particular shape at all, often because a nearby neighbor's gravity has pulled them apart. And then there are dwarf galaxies, small, faint, sometimes containing only a few million stars, the most common type in the universe and the easiest to overlook. If large galaxies are cathedrals, dwarfs are the small, forgotten chapels scattered everywhere around them. The important thing to notice is that shape is not permanent. It changes. A spiral can lose its gas and become a lenticular. A pair of spirals can merge and become an elliptical. A dwarf can be stretched and torn apart by the gravity of something larger. Whatever shape we see when we look at a galaxy is a snapshot, a single frame from a very long film. And tonight, we're going to watch that film unfold. Now let's move into one of the most beautiful features of a spiral galaxy, the arms themselves. And here's the first surprise. They're not what they appear to be. When you look at a spiral galaxy, the arms seem solid, rivers of stars flowing outward from the center. But they're not fixed structures. They're not made of a permanent group of stars moving together. They're patterns, waves of compression moving through the disk, and stars pass through them the way cars pass through a traffic jam. This idea is called density wave theory, and it was worked out in the 1960s by the astronomers Chia Lin and Frank Shu. Picture a highway where traffic slows in one section. Cars enter the slow zone, bunch up, then move on. The jam stays roughly in place, even though no individual car stays in it for long. Spiral arms work the same way. The wave moves through the galactic disk at one speed, and the stars orbit at another. When stars enter the compression zone, they crowd together and the arm appears brighter. When they pass through, they spread out again and fade into the dimmer space between the arms. So as we drift through a spiral arm right now, what we're really passing through is a region of compression, a zone where everything has temporarily gathered closer together. The stars around us will eventually move on, but the arm itself will remain. A persistent pattern maintained not by matter, but by motion. The arms are not things, they are processes, and there's something quietly wonderful about that. This solves a problem that troubled astronomers for decades. If spiral arms were made of the same stars, they'd wind up and disappear within about 1 billion years. That's called the winding problem. But density wave theory explains how the pattern persists far longer than any star remains within it. The shape endures, the contents flow through. And inside these arms, something remarkable happens. The same compression that creates the visible pattern also squeezes the gas drifting between the stars. When that gas is compressed enough, it can collapse under its own gravity. And when gas collapses, stars are born. This is why spiral arms glow blue. They're full of young, massive, freshly ignited stars. The arms aren't just patterns of crowding, they're engines of creation. As we pass through, we're walking through a place where new stars are being made, right now, all around us. Let's look more closely at the different kinds of spiral structure we might encounter. Some galaxies have what are called grand design spirals, two prominent, well-defined arms that you can trace for enormous distances around the disk. The Whirlpool Galaxy, Messier 51, is one of the most famous. Seen face-on from Earth, its two arms sweep outward in nearly perfect symmetry, studded with bright star-forming regions and threaded with dark lanes of dust. Grand design spirals are often shaped by the gravity of a nearby companion, which helps organize the pattern into something clean and elegant. Other spirals look more like something pulled apart. These are called flocculent spirals, from a word meaning fluffy or woolly. Instead of long sweeping arms, they have many short, patchy segments scattered across the disk, bright knots of star formation without a clear organizing pattern. NGC 4414 is a good example. In these galaxies, the structure is driven by local processes, pockets of star formation triggering further star formation nearby, rather than by a single large-scale wave, and some spirals fall in between. Our own Milky Way is thought to be somewhere in this middle range, a barred spiral with two major arms and several less prominent ones, its structure partially organized, but also shaped by local disturbances. If we were walking through it, we'd see order in some places and beautiful chaos in others. Let's pause at the center for a moment, because most spiral galaxies have something interesting here: a bar. About 2/3 of all spirals have one. It's an elongated concentration of stars stretching across the central region, with the spiral arms beginning at its ends. The Milky Way's bar is estimated to be about 27,000 light-years long. Bars aren't permanent. They can form, grow, weaken, and dissolve over billions of years, shaped by the gravitational push and pull between stars, gas, and dark matter. But while they exist, bars do something important. They act as funnels. They channel gas from the outer disk toward the center, redistributing material and energy within the galaxy. That funneled gas can pile up in the central regions, fueling bursts of star formation or feeding the supermassive black hole at the galaxy's heart. A bar is not just a shape, it's a mechanism, a piece of the galaxy's internal plumbing. Some astronomers think bars are a sign of maturity, a feature that develops as the disk settles and cools over time. Now let's pay attention to the motion around us. Every star in a spiral galaxy is in orbit around the galactic center. Our own sun moves at about 200 kilometers per second, completing one orbit every 225 to 250 million years, a period sometimes called a galactic year. In its entire existence, the sun has completed roughly 20 orbits. The dinosaurs last walked the Earth less than one galactic year ago. We are, cosmically speaking, on a very slow ride. One of the most important discoveries about this motion came in the 1970s, and it changed everything we thought we knew about galaxies. The astronomer Vera Rubin and her colleague Kent Ford set out to measure how fast stars orbit in spiral galaxies at different distances from the center. They expected something straightforward. In our solar system, planets closer to the sun orbit faster, and those farther out orbit slower. It follows from how gravity works when most of the mass is in one place. Rubin expected galaxies to behave the same way, but what she found was something else entirely. The rotation curves were flat. Stars far from the galactic center were orbiting just as fast as those closer in. That made no sense if the only matter in the galaxy was the visible stars and gas. There had to be far more mass, invisible mass, extending well beyond the visible disk, holding those outer stars in their fast orbits. This was some of the strongest evidence for the existence of dark matter, and it meant that when we step inside a galaxy, we are surrounded by something immense that we cannot detect with any of our senses. We now know that every large galaxy sits inside an enormous halo of dark matter that extends far beyond the visible disk. In the Milky Way, the disk is roughly 100,000 light-years across, but the dark matter halo may reach 600,000 light-years or more. An invisible sphere of gravitational influence 6 times wider than the galaxy you can see. The halo contains 5 to 10 times more mass than all the stars and gas combined. In a very real sense, the galaxy we can see is just the bright interior of an enormous dark structure. So as we explore tonight, keep in mind that most of what's here is hidden. The stars and gas and dust are beautiful, but they're the decorations on an invisible frame. The dark matter halo is the structure, the walls and floors and foundations of the building we're walking through. Dark matter halos aren't uniform. They're denser at the center and more diffuse toward the edges. Some simulations suggest they contain thousands of small, dense clumps, remnants of smaller halos absorbed as the galaxy grew. Whether all those clumps actually exist is still an open question, but the basic picture is clear. The halo provides the gravitational well in which the visible galaxy sits. It stabilizes the disk, influences how gas flows inward, and determines how the galaxy responds when it encounters something else. Understanding the halo is essential to understanding anything about the galaxy within it. Vera Rubin's flat rotation curves have since been confirmed in hundreds of galaxies. The pattern is remarkably consistent. Almost every spiral galaxy shows the same thing: high rotation speeds, extending far beyond the visible edge of the disk. It's one of the strongest arguments that dark matter is real. There are alternative ideas. A theory called modified Newtonian dynamics, or MOND, suggests that gravity itself behaves differently at very low accelerations, the kind found in the outer reaches of galaxies. MOND can explain flat rotation curves without dark matter, and it's had some successes. But it struggles with other observations, like the behavior of galaxy clusters and patterns in the cosmic microwave background. The debate continues quietly, but most astronomers currently favor dark matter as the explanation. Let's shift our attention now to what fills the space between the stars, because the gaps aren't empty. They're full of the interstellar medium, a thin, complex mixture of gas and dust that permeates the entire galaxy. Most of it is hydrogen, the simplest and most common element in the universe. Some is atomic hydrogen, drifting in cool, diffuse clouds. Some is ionized hydrogen, heated by nearby stars until its electrons have been stripped away. And some exists as molecular hydrogen, tucked inside dense, cold clouds where temperatures sit just a few degrees above absolute zero. These molecular clouds are where stars are born. They're vast, some stretch hundreds of light years across, and they're cold and dark, often invisible to optical telescopes. But in infrared and radio wavelengths, they reveal themselves. Carbon monoxide, water, ammonia, methanol, even complex organic molecules. The chemistry of these clouds is surprisingly rich for places that seem, at first glance, nearly empty. As we pass through one now, we're inside a stellar nursery. The raw material for future suns is all around us, slowly gathering, slowly cooling, waiting for the moment when gravity tips the balance and collapse begins. The interstellar medium is restless. It's constantly being stirred, heated, cooled, compressed, and scattered by the stars living within it. When a massive star explodes as a supernova, the blast wave sweeps through the surrounding gas, creating an expanding bubble of hot, thin material. These remnants can stretch dozens of light years across, compressing gas at their edges and sometimes triggering the formation of new stars. The death of one generation leads directly to the birth of the next. Stellar winds, streams of charged particles flowing from the surfaces of hot, luminous stars, carve their own cavities. In regions where many massive stars form together, these individual bubbles merge into enormous superbubbles spanning hundreds of light years. Walk far enough through a galaxy's disk, and you'd pass through these hollowed-out spaces, hot and thin and echoing with the energy of stars that burned brightly and briefly. At the edges, where the swept-up gas is piled thick, new stars are forming, the cycle continuing. Dust makes up a small fraction of the interstellar medium, but it leaves its mark everywhere. Interstellar dust grains are tiny, fractions of a micrometer across, but they're remarkably effective at absorbing and scattering starlight. This is what creates the dark lanes visible in many spiral galaxies, threading through the bright arms like shadowed corridors. Dust absorbs blue light preferentially, making distant stars appear redder than they truly are. Astronomers call this interstellar reddening, and they have to account for it whenever they measure the true colors and distances of stars. But dust grains do something even more important than block light. Their surfaces serve as tiny catalysts where atoms can meet and bond. The most crucial reaction that happens on a dust grain is the formation of molecular hydrogen. Two hydrogen atoms landing on the grain, finding each other, and bonding. Without dust, molecular clouds would be far less common, and star formation would proceed very differently. In a quiet, unnoticed way, these microscopic particles help build the stars. Walking through the interstellar medium, you'd never see them individually, but they're everywhere, and without them, the galaxy would be a very different place. Now here's something that ties everything together. The life of a galaxy is, at its core, a story about gas. Gas flows in from the surrounding environment, collects in the disk, cools and condenses into clouds, collapses into stars, and then, when those stars live and die, returns to the interstellar medium, enriched with heavier elements forged in stellar cores. This cycle is sometimes called the baryon cycle, and it's the heartbeat of a galaxy. As long as fresh gas keeps arriving, the galaxy can keep forming stars. When the gas runs out, or something prevents it from cooling, star formation slows and eventually stops. Let's follow this cycle as we move through. The rate at which a galaxy forms stars varies enormously over its lifetime. Some galaxies go through periods of intense creation called starbursts, producing new stars at 10 or even 100 times the normal rate. These bursts are often triggered by interactions with other galaxies, which compress the gas and drive it toward the center. The blue, clumpy galaxies visible in deep surveys of the early universe were forming stars at extraordinary rates, building up their mass in rapid, brilliant episodes. But starbursts can't last. They consume gas at unsustainable rates and produce enormous energy that heats and expels whatever gas remains. The burst is self-limiting, a fire that eventually exhausts its own fuel. This is one reason galaxies don't simply convert all their gas into stars at once. The process is regulated. Gravity pulls gas in. Energy from stars and black holes pushes it out. The balance between these forces determines how fast a galaxy builds. In a galaxy like the Milky Way, the current star formation rate is modest, roughly 1 to 2 solar masses of new stars per year. Spread across a disk 100,000 light-years wide, that's a gentle, steady process. New stars forming in scattered molecular clouds, each cloud producing a handful over millions of years. It's quiet work, unhurried, like a garden that blooms continuously rather than all at once. Star formation isn't spread evenly through a galaxy. It concentrates in the spiral arms, where gas is compressed by density waves, and in the central regions, where bar-driven inflows pile up fuel. The outer edges, where gas is thinner, form fewer stars. This creates a gradient, brighter and younger toward the center, dimmer and older at the edges. As you move outward through a galaxy's disk, you're moving through progressively older, quieter neighborhoods. Some galaxies have rings of star formation instead of arms. These can form when a smaller galaxy punches straight through the center of a larger one, sending an expanding wave of compression outward through the disk. like the ripple from a stone dropped in a pond. As the wave moves out, it triggers star formation along its front, creating a luminous ring of young, blue stars surrounding a quieter interior. The Cartwheel Galaxy, about 500 million light-years away, is one of the most spectacular examples. Step inside it, and you'd find yourself in a ring of creation expanding outward into the dark. At the opposite extreme, some galaxies are producing stars so furiously that the process dominates everything. Ultra-luminous infrared galaxies, or ULIRGs, are shrouded in dust that absorbs the light of billions of forming stars and re-radiates it in the infrared. They're among the most luminous objects in the universe, yet nearly invisible in optical light. Most are the result of violent mergers between gas-rich galaxies, where the collision has compressed enormous quantities of gas into the center, igniting a firestorm of creation behind thick curtains of dust. If you could somehow walk through one, you'd be surrounded by warmth and glow, but you wouldn't be able to see very far. Everything hidden behind veils of dust, everything burning. And then there are galaxies where the fire has gone out. Quenched galaxies, mostly ellipticals and some lenticulars, have used up or lost their gas supply. Star formation has almost entirely ceased. Their stellar populations are old. Their light is reddish, and the disks they may once have had are gone, transformed into smooth, featureless shapes. The transition from active to quenched is one of the big questions in galaxy evolution. What shuts a galaxy down? Several things can do it. Simply running out of gas, consuming it through star formation faster than new gas can flow in. Heating, energy from a supermassive black hole or from the hot gas in a galaxy cluster can heat the remaining gas so thoroughly it can never cool and collapse. Stripping. When a galaxy falls into a dense cluster, the hot surrounding gas can tear away its fuel like wind stripping leaves from a tree. This is called ram pressure stripping, and it can shut down star formation relatively quickly. Each quenching pathway leaves different signatures. By studying quenched galaxies in detail, astronomers can read the story of how each one lost its breath. Some were quenched suddenly, in dramatic events. Others faded gradually, their star formation declining over billions of years as gas trickled away. Walk through an elliptical galaxy today, and you're walking through something that was once busy and bright, but has slowly, quietly, wound down into a vast and gentle stillness. The color of a galaxy tells you where it is in this story. Blue galaxies are still forming stars. The blue comes from hot, massive, short-lived stars that dominate the light. Red galaxies have stopped. Their glow comes from older, cooler stars that have outlasted the blue giants. Between them sits a sparsely populated zone called the Green Valley, where galaxies are in transition. Crossing the Green Valley means a galaxy is either fading from blue to red, or, more rarely, reigniting from red toward blue if new gas arrives. The Green Valley isn't a destination, it's a corridor, and galaxies pass through it at different speeds, some in a rush, some lingering for 1 billion years. There's a pattern to all of this that surprised astronomers when they first noticed it. In the early universe, the most massive galaxies were forming stars at tremendous rates. But by a few billion years in, many of those massive galaxies had already quenched. Meanwhile, smaller galaxies kept forming stars for much longer. Some are still at it today. This is called downsizing, and it was unexpected. Simple models had predicted the opposite, that the biggest galaxies would take the longest to finish building. Instead, it's the giants that go quiet first. Downsizing suggests that the most massive galaxies have the most powerful quenching mechanisms. Perhaps they host the strongest supermassive black holes, or perhaps they sit in the densest environments where stripping is most effective. Whatever the cause, the result is a universe where the grandest galaxies are also the quietest, and the smallest, most overlooked ones are often still alive with creation. A galaxy's entire star formation history is written in its starlight. By carefully analyzing the light, astronomers can estimate the ages, compositions, and masses of the stars, building a picture of when and how much was created at each epoch. This technique, spectral energy distribution fitting, is a way of reading a galaxy's autobiography from the collective glow of its stars. Some galaxies formed most of their stars in a single intense burst long ago and have been fading ever since. Others have built steadily. A few have had episodic lives, bursts of activity separated by long, quiet intervals. The feedback from massive stars and supernovae is one of the most important regulators in all of this. When massive stars form, they pour out intense radiation and winds that heat and scatter the surrounding gas. When they explode, they inject even more energy into the interstellar medium. This feedback prevents gas from collapsing too efficiently. Without it, galaxies would convert their gas into stars far too quickly, exhausting their supply in a fraction of the time they actually take. The result is a kind of equilibrium. Gas flows in, forms stars, and the stars push back. The balance determines the star formation rate at any given time. Disturb the balance with a merger, a fresh inflow, a burst from the central black hole, and the rate shifts, sometimes dramatically. But the system returns to equilibrium, maintaining a steady pace. It's a kind of breathing. The galaxy inhaling gas, exhaling energy, over and over for billions of years. Let's move deeper now and look at how the galaxy changes chemically over time. The metallicity of a galaxy, the fraction of its mass in elements heavier than hydrogen and helium, increases as generations of stars forge new elements and scatter them into space. The first stars formed from nearly pure hydrogen and helium, the only elements produced in the Big Bang. Those early stars created the first carbon, oxygen, nitrogen, silicon, and iron in their cores, and released them when they died. Each generation after that started with a slightly richer mix and produced more. Younger stars contain more heavy elements than older ones, a relationship astronomers use to estimate ages. Our sun is relatively metal-rich, which tells us it formed from gas already processed through several earlier generations. We are, in a sense, walking through a galaxy that has been composting itself for billions of years, each generation of stars enriching the soil for the next. This enrichment matters far beyond the galaxy itself. Carbon, oxygen, nitrogen, silicon, iron, the elements of rocky planets and living organisms were all forged inside stars. A galaxy's ability to form habitable worlds depends on how many stellar generations have come and gone. We owe our existence not just to one star, but to a long lineage stretching back through the galaxy's chemical history. In the outer reaches, where fewer stars have formed, the metallicity is lower. In the dense central regions, it's higher. This gradient is another way of reading the galaxy's story. The center has been active longer, while the outskirts remain more pristine. Walking from edge to center is like walking forward through time, from simpler chemistry to richer, more complex compositions. The chemical history is also shaped by flows of gas in and out. Gas arriving from the intergalactic medium is typically metal poor, nearly pristine material that has never been inside a star. This inflow dilutes the metallicity, especially in the outer disk. Meanwhile, galactic winds driven by supernovae and black holes can expel metal-enriched gas entirely, carrying the products of stellar nucleosynthesis out into the circumgalactic medium, the vast halo of gas surrounding the galaxy. Let's step out there for a moment. The circumgalactic medium extends hundreds of thousands of light years beyond the visible disk. It's hot, diffuse, and nearly invisible, but it may contain as much gas as the disk itself. It's a reservoir, a recycling plant, and a boundary all at once. Gas expelled by galactic winds enters this halo, cools over millions of years, and can eventually fall back into the disk, fueling new star formation. At the same time, fresh gas from the intergalactic medium passes through on its way in. This creates a fountain-like circulation. Gas heated by stellar feedback rises into the halo, cools, and falls back as fresh fuel. A single cycle can take hundreds of millions of years, but it's continuous. Without it, many spiral galaxies would have exhausted their gas supply long ago. The fountain keeps the galaxy alive, circulating matter through an enormous loop that connects the disk, the halo, and the space beyond. Standing out here in the circumgalactic medium, you'd feel nothing. The gas is far too thin. But you'd be inside one of the most important systems in the galaxy's life, the quiet machinery that keeps everything running. Some gas arrives not through recycling, but through cold accretion. Streams of cool gas flowing directly from the intergalactic medium along the filaments of the cosmic web. These cold flows can penetrate deep into the halo without being heated, delivering fuel straight to the disk. Cold accretion was especially important in the early universe when galaxies were growing fast and needed enormous amounts of gas. Today it still occurs, but at lower rates. The surrounding gas is hotter now, making it harder for cold streams to survive the journey inward. This decline may be one reason star formation rates across the universe have been falling for the past 10 billion years. The cosmic supply of fresh, cold gas is slowly running out. The balance between inflow, star formation, and outflow determines the entire trajectory of a galaxy's life. A galaxy that keeps receiving fresh gas can keep forming stars indefinitely. One that loses its supply will slowly fade as existing stars age, and nothing replaces them. Every galaxy's fate is written in its gas, and the forces that control that supply, gravity, feedback, environment, the slow thinning of the cosmic web, are among the most important in all of astrophysics. And so the life of a galaxy unfolds through this quiet cycling of gas and stars, each generation building on the one before, each supernova both an ending and a beginning. The galaxy breathes, not with lungs, but with gravity and light and the slow redistribution of matter across a disk 100,000 light years wide. It's a rhythm measured not in seconds or years, but in hundreds of millions of years. A heartbeat so slow that entire civilizations could rise and fall between pulses, never knowing the galaxy around them was alive with motion and change. And here we are, drifting through it, noticing what we can, listening to the quiet. There's much more ahead. Let's move toward the center now. We've been drifting through the disk, through spiral arms and molecular clouds, through dust lanes and star-forming regions. But every large galaxy has something at its heart, and the deeper we go, the more crowded and luminous the surroundings become. Stars pack more tightly here. The light thickens, and at the very center, hidden behind all that glow, sits something extraordinary, a supermassive black hole. Nearly every large galaxy we've ever examined has one. Not a stellar mass black hole, the kind left behind when a single massive star collapses. Those are scattered throughout the disk by the millions. This is something else entirely. A supermassive black hole contains millions, or even billions of times the mass of the Sun, compressed into a region smaller than our solar system. The one at the center of the Milky Way, called Sagittarius A star, has a mass of roughly 4 million suns. It sits there quietly, surrounded by a dense swarm of stars orbiting at tremendous speeds. Some of those stars have been tracked for decades, their paths traced with extraordinary precision, and it was this patient tracking that confirmed the black hole's existence and won the astronomers involved a Nobel Prize. 4 million solar masses is large by any human standard, but among supermassive black holes, Sagittarius A star is modest. The black hole at the center of Messier 87, the giant elliptical galaxy in the Virgo cluster, has a mass of about 6.5 billion suns. That's more than 1,000 times the mass of ours. And in 2019, the Event Horizon Telescope captured the first ever image of that black hole's shadow, a dark silhouette ringed by glowing gas, light bending around the edge of something from which nothing escapes. It was the first time we had ever seen the shape of the unseeable. As we approach the center of a galaxy, the black hole itself is invisible. It emits no light, but its influence is everywhere. Stars near the center orbit faster. Gas spiraling inward heats up and glows. And in some galaxies, not all, but some, the black hole is actively feeding, pulling in material and releasing staggering amounts of energy in the process. When that happens, the galaxy's center lights up, and what was a quiet heart becomes one of the most powerful engines in the universe. This is what astronomers call an active galactic nucleus, or AGN. The mechanism is relatively straightforward in principle, though extraordinarily violent in practice. Gas falling toward a supermassive black hole doesn't simply drop in. It spirals inward, forming a disk of superheated material called an accretion disk. Friction within this disk heats the gas to millions of degrees, causing it to radiate intensely across the electromagnetic spectrum, from radio waves to X-rays. The energy output of a luminous AGN can exceed the combined light of every star in the entire galaxy. A single engine at the center, no larger than our solar system, outshining hundreds of billions of stars. The most extreme AGN are called quasars. These are found primarily in the distant universe, which means we're seeing them as they were billions of years ago, when the universe was younger and galaxies were still assembling. Quasars are so bright that they were initially mistaken for nearby stars. The word quasar is short for quasi-stellar object. Some quasars are visible across most of the observable universe, their light traveling for more than 12 billion years to reach us. They are beacons, marking the locations of young, vigorously feeding black holes and galaxies that were still in the process of growing. Not all AGNs are quasars. There's a whole spectrum of activity. Seyfert galaxies have moderately active nuclei, bright enough to be detected but not overwhelming. Radio galaxies produce powerful jets of material that stream outward from the central engine at nearly the speed of light, extending hundreds of thousands of light years into the surrounding space. Blazars are AGN, whose jets happen to point almost directly at Earth, making them appear extraordinarily bright and rapidly variable. All of these are different views of the same basic phenomenon: a supermassive black hole consuming gas and releasing energy, seen from different angles, at different feeding rates, and in different types of host galaxies. The jets produced by some AGN are among the most spectacular structures in the universe. They are beams of plasma, accelerated to nearly the speed of light, launched from the region just outside the black hole's event horizon and channeled outward along the galaxy's magnetic field lines. These jets can extend for hundreds of thousands of light years, far beyond the visible boundaries of the galaxy itself, punching into the intergalactic medium and inflating enormous lobes of hot, magnetized gas. The radio galaxy Cygnus A, about 600 million light-years away, has jets that stretch for nearly 300,000 light-years on either side, ending in bright hotspots where the jet material slams into the surrounding medium. Standing near one of these jets, if you could survive, which you certainly could not, you would see a narrow beam of material hotter and faster than almost anything else in the universe, cutting through the galaxy like a searchlight through fog. The jet does not merely radiate energy, it physically pushes the gas around it, clearing channels through the interstellar and intergalactic medium, heating the surrounding material, and preventing it from cooling and forming stars. This is one of the ways a supermassive black hole regulates its host galaxy, not by consuming everything, but by heating the environment and throttling the supply of gas available for star formation. This process is called AGN feedback, and it's one of the most important concepts in modern galaxy evolution. Without it, the most massive galaxies would have far more stars than they actually do. Simulations that leave out AGN feedback produce galaxies that are too massive, too blue, and too actively star-forming. When feedback is included, the black hole periodically heats and expels gas from the central regions, suppressing star formation and keeping the galaxy's growth in check. The black hole acts as a thermostat. When too much gas accumulates and begins to fuel star formation, some of that gas also feeds the black hole, which responds with an outburst that pushes the gas away. When the outburst fades, gas can begin to accumulate again, and the cycle repeats. This feedback cycle operates on timescales of tens to hundreds of millions of years, and it creates a self-regulating relationship between the black hole and its galaxy. Grow too quickly, and the black hole intervenes. Calm down, and accumulation resumes. The result is that the mass of the central black hole is closely correlated with the mass and velocity dispersion of the galaxy's central bulge. Bigger galaxies have bigger black holes, in a relationship so tight that it suggests the two have been co-evolving, growing together, each influencing the other's development across billions of years. This relationship was one of the great surprises of the late 20th century. The black hole at the center of a galaxy is tiny compared to the galaxy as a whole. Its sphere of gravitational influence extends only a few hundred light years at most, a minuscule fraction of a galaxy that might span 100,000 light years. And yet the black hole's mass knows about the galaxy's mass. The galaxy's bulge knows about the black hole. Something connects them across scales, separated by factors of millions. That something, we now believe, is feedback. The black hole and the galaxy have been in conversation for most of their shared history, each shaping the other through the language of gas and energy. Not all supermassive black holes are actively feeding. In fact, most aren't. Sagittarius A star at the center of our own galaxy is remarkably quiet. It accretes matter at an extremely low rate and produces very little radiation compared to what it could if more gas were available. It's dormant, like a furnace with no fuel. But dormancy is not death. If new gas were directed toward the center, by a galactic merger, a bar-driven inflow, or the disruption of a passing gas cloud, the black hole could reawaken. There's evidence that Sagittarius A star was much more active in the past. Enormous bubbles of hot gas, called Fermi bubbles, extend above and below the galactic plane of the Milky Way, spanning roughly 50,000 light years. These may be the remnants of an energetic outburst from the central black hole millions of years ago, a reminder that even quiet hearts can roar. The duty cycle of a supermassive black hole, the fraction of time it spends in an active state, varies from galaxy to galaxy. Some black holes are active for relatively brief episodes, flaring up for a few million years before settling back to dormancy. Others, particularly in the most massive galaxies, may cycle through repeated episodes of activity over billions of years, each outburst suppressing star formation for a while before the gas supply gradually rebuilds. The cumulative effect of many such episodes can be profound, slowly transforming a galaxy's star formation rate gas content, and even its structure over cosmic time. In some galaxies, the black hole's influence is visible in a particularly dramatic way. At the centers of many galaxy clusters, the hot intracluster gas should be cooling rapidly, losing energy through X-ray radiation and condensing into the central galaxy, where it would fuel enormous bursts of star formation. This was predicted by early theoretical models and is called a cooling flow. But observations showed that the expected cooling was not happening, or at least not at the predicted rates. Something was keeping the gas hot. That something turned out to be the central black hole. In many cluster centers, radio observations revealed jets and lobes from the AGN that are inflating bubbles in the hot intracluster gas, like a slow-motion explosion unfolding over millions of years. These bubbles rise buoyantly through the cluster atmosphere, carrying energy outward and stirring the gas, preventing it from cooling efficiently. The black hole at the center of the Perseus cluster, for example, has carved enormous cavities in the X-ray emitting gas, each one tens of thousands of light years across. The energy needed to inflate these cavities is staggering, roughly equivalent to the total energy output of the Sun over billions of years, delivered in each cavity. This is AGN feedback operating on the largest scales, a single black hole at the center of a single galaxy, regulating the behavior of gas that fills an entire galaxy cluster. It is remarkable in its reach. A compact object smaller than our solar system influencing an environment millions of light years across. And it happens not through a single dramatic event, but through a gentle, persistent, rhythmic process. Inflate, rise, stir, wait, inflate again. Let's pull back now and look at another part of a galaxy's life, the way galaxies interact with their neighbors. Because no galaxy exists in true isolation. Every galaxy is part of a larger community, a group, a cluster, a filament of the cosmic web, and its life is shaped profoundly by the company it keeps. The most common form of galactic interaction is what you might call nibbling. Large galaxies are surrounded by smaller companions, dwarf galaxies, satellite galaxies, little collections of stars and gas that orbit within the larger galaxy's dark matter halo. And over time, the larger galaxy consumes them. One by one, the smaller companions spiral inward, stretched and pulled apart by tidal forces, their stars and gas absorbed into the larger system. This is galactic cannibalism, and it's been happening for as long as galaxies have existed. The Milky Way is doing it right now. Our galaxy has at least 50 known satellite galaxies, most of them small dwarf galaxies containing only a few million or a few billion stars. The two largest are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light. The Magellanic Clouds are substantial galaxies in their own right. The Large Magellanic Cloud contains roughly 30 billion stars. But they are small compared to the Milky Way, and they are being slowly drawn into our galaxy's gravitational embrace. A stream of gas called the Magellanic Stream trails behind the clouds, stretching more than 100 degrees across the sky. This stream was pulled from the clouds by tidal forces and by the interaction between the clouds and the Milky Way's circumgalactic medium. It's a visible sign that the clouds are being altered by their proximity to a larger neighbor. Whether they will eventually be fully consumed or escape back into the wider universe is still debated, but their current trajectory suggests they have been falling toward the Milky Way and may be on their first close passage. Other satellite galaxies have already been torn apart. The Sagittarius Dwarf Elliptical Galaxy, located on the far side of the Milky Way from our position, has been stretched into a long tidal stream that wraps around our galaxy multiple times. It has already lost much of its original mass, and its remaining core is slowly being shredded. In a few 100 million years, it will cease to exist as a distinct galaxy. its stars will be scattered throughout the Milky Way's halo, absorbed so completely that only careful analysis of stellar motions and compositions will reveal they were ever part of a separate system. These tidal streams are some of the most beautiful structures in galactic astronomy. They are long, thin ribbons of stars stretched across the sky, tracing the orbital paths of disrupted galaxies. Each stream tells the story of a galactic meal, a smaller system that wandered too close, was caught by gravity, and was slowly pulled apart like taffy. The streams can span enormous distances, wrapping partly or fully around the host galaxy, and their shapes encode information about the mass and structure of the dark matter halo through which they move. By studying tidal streams, astronomers can map the invisible gravitational landscape of a galaxy with remarkable precision. The Milky Way's halo is laced with these streams. The Sagittarius stream is the most prominent, but others have been identified. The Orphan stream, the GD1 stream, the Palomar 5 stream, and more. Each one is the ghostly remnant of a galaxy or star cluster that was consumed. Together, they form a record of the Milky Way's feeding history, written in starlight across the sky. Walking through the halo tonight, we'd be passing through the scattered remains of galaxies that no longer exist. Their stars still orbiting, still shining, but no longer part of the communities that once held them together. The rate of galactic cannibalism has changed over cosmic time. In the early universe, when galaxies were closer together and dark matter halos were still assembling, mergers and accretions were more frequent. The hierarchical model of galaxy formation holds that large galaxies were built from the mergers of many smaller ones. Each large galaxy is, in a sense, a composite of dozens or hundreds of smaller systems that were absorbed over billions of years. The Milky Way, for all its apparent unity, is a patchwork. Its stars come from many different origins, gathered over time into a single, coherent structure. Galactic cannibalism doesn't just add stars. It also brings in gas, dark matter, and sometimes globular clusters, dense, ancient balls of stars that orbit in a galaxy's halo. Many of the Milky Way's roughly 150 known globular clusters may have originated in other galaxies, brought in as part of accretion events. Some globular clusters have chemical compositions that are distinctly different from the majority of Milky Way stars, suggesting they formed in a different environment. These clusters are immigrants, stellar communities that were born elsewhere and absorbed into a larger society. The absorption of dwarf galaxies can also trigger star formation in the host. When a gas-rich dwarf galaxy falls into a larger spiral, its gas can be compressed by the encounter, forming new stars either in the dwarf itself or in the disk of the host galaxy where the fresh gas settles. Some of the youngest star-forming regions in the Milky Way's outer disk may have been fueled by gas stripped from incoming satellites. In this way, cannibalism is not purely destructive. It also delivers raw material for new creation. Let's pause for a moment on the dwarf galaxies themselves, because they are some of the most fascinating and underappreciated objects in the universe. Dwarfs come in many varieties. Dwarf irregular galaxies are small, shapeless collections of stars and gas, often actively forming new stars. Dwarf ellipticals are smooth, rounded, and gas-poor, their star formation long since finished. And then there are the ultra-faint dwarfs, ghostly collections of only a few thousand stars, so dim and diffuse that they are almost invisible even to modern telescopes. These ultra-faint dwarfs may be the most dark matter-dominated objects in the universe. They're tiny collections of stars embedded in dark matter halos far more massive than the visible component would suggest. Dwarf galaxies are believed to be the building blocks from which larger galaxies were assembled. In the early universe, The first gravitationally bound structures were small, clumps of dark matter containing modest amounts of gas, forming the first small galaxies. Over time, these small systems merged and accreted, growing into the larger galaxies we see today. The dwarf galaxies that survive today are those that, for one reason or another, avoided being absorbed, either because they orbit at large distances from their host, or because they arrived late, or because their orbits carry them through regions where tidal forces are weaker. Some dwarf galaxies have had remarkable histories despite their small size. The Large Magellanic Cloud, though classified as a dwarf irregular, has a mass of about 10 billion solar masses and contains active star-forming regions, including the Tarantula Nebula, one of the most vigorous stellar nurseries in the entire local group. The small Magellanic Cloud, even tinier, has been a laboratory for understanding how star formation and galactic structure work in low-mass, low-metallicity environments. These are not minor objects. They are worlds unto themselves, each with a unique story. Tidal interactions between dwarf galaxies and their hosts can produce structures beyond simple streams. When a dwarf galaxy passes through the disk of a larger galaxy, the encounter can warp the disk, create rings, or excite spiral structure. The Milky Way's disk is slightly warped. It bends upward on one side and downward on the other, and this warp may have been caused or amplified by the gravitational influence of the Magellanic Clouds. The disk also shows vertical oscillations, like ripples on a pond, that may trace the passage of a satellite galaxy through the disk in the past. These disturbances are temporary on cosmic timescales. The disk will eventually settle back to a flatter state as the perturbation dissipates. But while they last, they are visible signatures of interaction, proof that the galaxy is not a closed system, but one that is constantly being nudged, tugged, and shaped by its surroundings. Walking through the Milky Way's disk tonight, we'd feel none of this. The warps and ripples unfold over millions of years, but they are there, recorded in the positions and motions of billions of stars, a quiet testament to the galaxy's ongoing relationship with its companions. The dark matter halos of galaxies extend far beyond the visible boundaries, and when galaxies interact, it is the halos that meet first. In a minor merger, the absorption of a small galaxy by a large one, the smaller halo is gradually stripped away as it orbits within the larger halo. The dark matter is dispersed into the host's halo, adding to its mass and slightly altering its profile. This stripping can take billions of years, occurring gradually as the satellite's orbit decays through a process called dynamical friction, the gravitational drag created by the satellite's wake as it moves through the host's dark matter. Dynamical friction is a beautiful concept. As a satellite galaxy moves through a dark matter halo, it gravitationally attracts the surrounding dark matter particles, creating a region of slightly higher density behind it, a gravitational wake. This wake pulls backward on the satellite, slowing it down and causing its orbit to shrink over time. Eventually, the satellite spirals inward and merges with the central galaxy. The timescale depends on the mass ratio. More massive satellites experience stronger friction and merge faster. Small satellites at large distances can orbit for many billions of years before finally falling in. The process of dynamical friction explains why galaxy groups and clusters evolve over time. In a galaxy group, the member galaxies gradually lose orbital energy and spiral toward the center, where they merge with the central dominant galaxy. This is why the largest galaxies in groups and clusters, the brightest cluster galaxies, or BCGs, are so massive. They have been growing for billions of years by absorbing their neighbors, one by one. The BCG at the center of the Coma cluster, NGC 4889, is one of the largest galaxies known. with a mass of several trillion solar masses, and it continues to grow as more satellites fall in. The growth of galaxies through accretion is not always smooth. Sometimes a galaxy accretes a companion that is large enough to cause significant disturbance, but not large enough to be considered a major merger. These intermediate encounters, sometimes called minor mergers, can thicken the disk, puff up the bulge, trigger modest bursts of star formation, and leave behind shells and ripples in the outer regions of the host galaxy. Shells are particularly striking. They are faint arcs of starlight that appear concentrically around elliptical and lenticular galaxies, believed to be the debris from a minor merger in which the smaller galaxy was disrupted and its stars now oscillate back and forth on radial orbits, piling up at the turning points to create visible shell structures. The galaxy NGC 3923 is one of the most beautiful examples. It has more than 20 identified shells, nested inside each other like the rings of an onion. Each shell marks a turning point in the orbit of disrupted stellar material. The spacing and brightness of the shells encode information about the potential well of the host galaxy and the time since the merger occurred. Reading the shells is like reading the rings of a tree. Each one marks a moment in the galaxy's life. Ripples are similar to shells, but appear in disk galaxies rather than ellipticals. When a satellite galaxy plunges through a disk, it creates concentric ring-like disturbances that propagate outward, like the ripples from a stone dropped in water. These ripples fade over time but can persist for hundreds of millions of years, visible in deep imaging as faint corrugations in the disk's light. The Milky Way itself may have such ripples, created by past encounters with satellite galaxies. Galaxy interactions also redistribute angular momentum, the rotational energy stored in a galaxy's spinning disk. When a satellite falls in, the gravitational interaction can transfer angular momentum from the satellite to the disk, or from the disk to the halo, altering the galaxy's rotation profile. This redistribution is subtle and unfolds over long timescales, but its cumulative effect can change the structure of the galaxy significantly. Bars, for instance, are efficient at redistributing angular momentum, transferring it from the inner disk to the outer disk and halo, which causes the bar to slow down and the disk to evolve. Angular momentum is one of the fundamental quantities that determines a galaxy's structure. A galaxy with high angular momentum forms a large, thin, extended disk. One with low angular momentum forms a compact, centrally concentrated structure. The angular momentum of a galaxy is largely set during its formation, determined by the torques exerted on the collapsing dark matter halo by its neighbors. But it is not fixed. Mergers, interactions, and internal processes can redistribute angular momentum throughout a galaxy's life, gradually reshaping its structure. Let's wander now into the spaces between galaxies within a group. Galaxy groups are the most common galactic environments, loose collections of a few to a few dozen galaxies bound together by their mutual gravity. The local group, which contains the Milky Way, Andromeda, and about 80 smaller galaxies, is a typical example. Groups are modest in size compared to clusters, but they are where most galaxies live, and the interactions within groups shape galactic evolution in important ways. Within a group, galaxies move at relatively modest speeds, a few hundred kilometers per second, compared to the 1,000 or more kilometers per second typical of galaxies in large clusters. This means that when galaxies in a group encounter each other, the interactions are slow enough for gravity to have a strong effect. Galaxies can become tidally distorted, exchange gas, trigger star formation in each other, and eventually merge. The slow, intimate interactions in groups are where much of the interesting evolutionary action occurs. The local group is in the early stages of one such interaction. The Milky Way and the Andromeda Galaxy are currently separated by about 2.5 million light-years, but they are approaching each other at roughly 110 kilometers per second. In about 4 to 5 billion years, they will have their first close encounter, and eventually, over the course of a few billion more years, they will merge into a single, larger galaxy. But we'll explore that story later. For now, it's enough to know that the Milky Way's future, like its past, is defined by its relationships with its neighbors. Galaxy groups can evolve over time into what are called fossil groups, systems in which all the member galaxies have merged into a single dominant galaxy, leaving behind a lone, massive elliptical surrounded by only very small companions. Fossil groups are thought to represent the end state of group evolution, the result of billions of years of dynamical friction and merging. They are quiet, settled systems, galaxies that have finished their social lives and now sit alone in their dark matter halos, surrounded by hot gas and a few faint satellites. The hot gas in groups is called the intragroup medium, and it plays a role similar to the intracluster medium in larger systems, though it is cooler and less dense. Galaxies moving through this gas can experience ram pressure stripping, though the effect is generally weaker in groups than in clusters. Still, even modest stripping can reduce a galaxy's gas content over time, slowly suppressing its star formation. Some of the red quenched galaxies seen in groups may owe their state partly to this gentle, persistent stripping. Not a dramatic removal, but a slow erosion of their fuel supply over billions of years. Pre-processing is a term used to describe the environmental effects that occur in groups before those groups fall into larger clusters. Many galaxies that arrive in clusters have already been partially quenched or morphologically transformed by their time in a group. By the time they join the cluster, they have already lost some gas, experienced some tidal disturbance, and perhaps undergone a merger or two. The cluster environment then continues the process, finishing what the group began. Understanding pre-processing is important because it means that the diversity of galaxies we see in clusters today reflects not just the cluster environment, but also the prior lives of its members in smaller groups. Let's follow one more thread before we pause. When dwarf galaxies are consumed by larger hosts, the stars of the dwarf don't simply vanish. They become part of the stellar halo, the diffuse, roughly spherical distribution of stars that surrounds the main disk of a galaxy. The stellar halo of the Milky Way is faint. It contains only about 1% of the galaxy's total stellar mass, but it is immensely valuable as a record of the galaxy's accretion history. Many of the halo stars were born in other galaxies and later absorbed. Their orbits, chemical compositions, and ages carry information about where they came from and when they arrived. Galactic archaeology is the name given to the effort to reconstruct a galaxy's history from the detailed properties of its stars. By measuring the positions, velocities, and chemical abundances of millions of individual stars, astronomers can identify groups of stars that share common origins. Stellar streams from disrupted satellites, clumps of chemically similar stars that form together, and kinematic structures that trace past accretion events. It is forensic work, patient and meticulous, assembling the biography of the galaxy one star at a time. The European Space Agency's Gaia mission has been transformative for this field. Launched in 2013, Gaia has measured the positions and motions of nearly 2 billion stars in the Milky Way with unprecedented precision. Its data have revealed structures in the Milky Way's disk and halo that were previously invisible. Streams, shells, moving groups, and kinematic substructures that tell the story of past mergers and interactions. One of the most significant discoveries from Gaia is the Gaia Enceladus structure, also called the Gaia sausage, the debris of a substantial galaxy that merged with the Milky Way roughly 10 billion years ago. The stars of this ancient merger are spread throughout the inner halo, their orbits highly elongated, their chemical compositions distinct from the stars that formed within the Milky Way itself. The Gaia-Enceladus merger was a major event in our galaxy's history. The incoming galaxy had a mass roughly equivalent to 1/4 of the Milky Way's mass at the time, large enough to significantly disturb the disk, thicken it, and deposit a large population of stars into the halo. Some astronomers believe this merger may have helped trigger the formation of the Milky Way's thick disk, the puffier, older component that lies above and below the thin disk where most current star formation occurs. If so, the Milky Way's structure today bears the imprint of a collision that happened when the universe was less than 4 billion years old. Other ancient mergers have been identified in the Gaia data as well. The Sequoia merger, the Helmi streams, the Kraken merger, each one representing a distinct accretion event, a separate galaxy that was absorbed into the Milky Way at some point in its past. Together, these discoveries are building a picture of the Milky Way as a galaxy that has been assembled from many pieces. Its halo in particular, a mosaic of foreign stars woven together over billions of years. Walking through the stellar halo tonight, we're surrounded by immigrants. Stars born in galaxies that no longer exist, now orbiting quietly within a galaxy they were never originally part of. Their light is the same as any other stars, but their origins lie elsewhere, in smaller, older, now vanished systems that contributed their stars to the larger whole. There's something quietly moving about that. The galaxy is not one thing. It is many things gathered together, orbiting in a shared home, carrying within them the memory of places that are gone. So far, we've been exploring interactions between galaxies of very different sizes, large galaxies absorbing smaller companions, nibbling at dwarfs, pulling apart satellites. But sometimes two galaxies of roughly equal size meet. And when that happens, the encounter is transformative. Everything changes. Let's step into a major merger and see what it looks like from the inside. The first thing to understand is that galaxy mergers are slow, unimaginably slow. Two galaxies don't collide the way cars collide. They drift toward each other over hundreds of millions of years, drawn by gravity. Their dark matter halos overlapping long before their visible disks make contact. The initial approach might take 1 billion years. The first close passage, when the two galaxies sweep through each other, takes tens of millions of years. And the full process, from first encounter to final coalescence, can stretch across 2 to 3 billion years. Nothing about it is sudden. If you were living on a planet inside one of the merging galaxies, you would never feel it. The timescales are so vast that the entire history of human civilization would fit inside a single frame of the encounter. But slow does not mean gentle. As the two galaxies approach, their mutual gravity begins to distort them. Tidal forces, the difference in gravitational pull between the near side and the far side of each galaxy, stretch and warp the disks. Stars are pulled into long tidal tails that extend hundreds of thousands of light years into the surrounding space, arcing outward like the arms of dancers spinning apart. Gas is compressed. Shock waves ripple through the interstellar medium, and enormous bursts of star formation ignite across both galaxies. From a distance, a merging pair of galaxies can look like a cosmic explosion unfolding in slow motion. Tails streaming, bridges of gas connecting the two systems, bright knots of new stars scattered across the disturbed landscape. The antennae galaxies, about 60 million light-years away, are one of the most famous examples of a major merger in progress. Two spiral galaxies, NGC 4038 and NGC 4039, are currently in the process of colliding, and their interaction has produced two enormous tidal tails that stretch for hundreds of thousands of light years, giving the system its insect-like appearance. Within the overlap region, where the disks of the two galaxies intersect, the gas has been compressed to extraordinary densities, triggering one of the most intense episodes of star formation in the nearby universe. Thousands of young star clusters have formed in this region, many of them massive enough to eventually become globular clusters. The antennae are a factory of creation, powered by the gravitational energy of two galaxies falling into each other. The mice galaxies, NGC 4676, offer another snapshot. Two spirals caught in the act of their first close passage, their long tidal tails streaming behind them like the tails of mice running side by side. The mice are earlier in the merger process than the antennae, their disks still somewhat intact, but visibly distorted. In a few 100 million years, they will swing back toward each other, pass through again, and eventually merge into a single system. Watching the mice is like seeing the future of the antennae, or for that matter, the future of the Milky Way and Andromeda. Here's a remarkable thing about major mergers. Despite all the distortion and compression and energy, individual stars almost never collide. The distances between stars are so vast compared to their sizes that two galaxies can pass directly through each other with virtually no stellar collisions. If you shrank a star like the Sun down to the size of a grain of sand, the nearest neighboring grain would be several miles away. Stars are separated by gulfs of emptiness so enormous that even when billions of them occupy the same space during a merger, they simply sail past each other. The gas, however, does collide. It cannot pass through itself the way stars can. Gas from the two galaxies meets, shocks, heats, compresses, and fuels the dramatic star formation that makes mergers so visually spectacular. As the merger progresses, the ordered rotation of the original disks is gradually destroyed. Stars that once followed neat circular orbits are flung onto chaotic, random trajectories by the fluctuating gravitational field. The flat, spinning disk structure is scrambled into a rounder, puffier shape. Gas is driven toward the center by gravitational torques, fueling both a central starburst and, often, the accretion activity of the supermassive black holes. The two black holes from the original galaxies sink toward the center of the merged system through dynamical friction, eventually forming a binary pair that spirals inward over millions of years. In the final stages, the two black holes merge into one, releasing a burst of gravitational waves, ripples in the fabric of space-time itself that propagate outward at the speed of light. This final coalescence of the black holes is one of the most energetic events in the universe. Yet it is invisible to optical telescopes. Only gravitational wave detectors can sense it. The product of a major merger between two spiral galaxies is, in most cases, an elliptical galaxy. The ordered rotation is gone. The thin disk is gone. The spiral arms are gone. What remains is a smooth, roughly spherical or elongated collection of stars on random orbits supported not by rotation, but by the random motions of its stars. What astronomers call velocity dispersion. The transformation is profound. Two flat, structured, actively star-forming systems have become a single round, featureless, quiescent one. The gas has been largely consumed in the merger-driven starburst or expelled by the energy of supernovae and AGN feedback. Without gas, no new stars can form. The elliptical galaxy is born old, its stellar population dominated by whatever stars were created during and before the merger, aging quietly from that point forward. This is one of the main pathways by which elliptical galaxies are thought to form, through the merging of spirals. It's not the only pathway. Some ellipticals may have formed very early in cosmic history, from the rapid collapse and conversion of enormous gas reservoirs before disk structures had time to develop. Others may have been built through the cumulative effect of many minor mergers rather than a single dramatic event, but the spiral merger pathway is well established, supported by both observations and simulations, and it explains many of the properties we see in elliptical galaxies today. Let's step inside one. After the drama of the merger, an elliptical galaxy is a profoundly quiet place. The stars orbit on random paths, streaming in every direction, some radially, plunging toward the center and back out again, others on more circular paths, others on everything in between. There is no preferred plane of rotation, no disk, no arm structure. The light is smooth and even, brighter in the center and fading gradually toward the edges. The color is warm, yellows, oranges, the soft reddish glow of old, cool stars. There are very few young blue stars because there is very little gas from which to make them. The interstellar medium is almost empty. Dust lanes are rare. Molecular clouds are sparse or absent. Walking through an elliptical galaxy, you would feel a strange stillness. Not that the stars aren't moving, they are at hundreds of kilometers per second. But there is no coherent flow, no grand spiral pattern, no visible structure to anchor your sense of direction. Everything looks the same in every direction. It's like wandering through a vast, warm, featureless hall lit by billions of aging candles. Beautiful in its way, peaceful, but unmistakably different from the busy, structured workshop of a spiral. Elliptical galaxies span an enormous range of sizes. At the small end are the dwarf ellipticals, containing only a few billion stars and spanning a few thousand light years. At the large end are the giant ellipticals and their even more massive cousins, the CD galaxies, enormous diffuse systems that sit at the centers of galaxy clusters. The largest of these contain several trillion stars and extend for hundreds of thousands of light years, their outer envelopes blending into the intracluster light, a diffuse glow produced by stars that have been stripped from their parent galaxies and now drift freely through the cluster. The most massive ellipticals are among the oldest galaxies in the universe. Their stars formed billions of years ago, many of them within the first few billion years of cosmic history. These galaxies assembled their mass early, through a combination of rapid star formation and hierarchical merging, and have been slowly fading ever since. They are the retired elders of the galaxy population, enormous, venerable, and quiet. Their star formation histories, read from the light of their aging stellar populations, tell of an intense youth followed by a long, calm maturity. Inside a giant elliptical, the stellar population is not entirely uniform. Careful observations reveal subtle gradients. The stars near the center tend to be slightly redder, older, and more metal-rich than those in the outer regions. This is consistent with a picture in which the central regions formed first and most intensely, while the outer envelope was built up later through the accretion of smaller galaxies. The gradient is a geological record, like sedimentary layers. The deeper you go, the older and richer the material. Some elliptical galaxies contain faint remnants of their merger origin. Shells, ripples, and faint tidal features can persist for billions of years, slowly fading as the stars spread out on their orbits. Deep imaging surveys have revealed that many apparently smooth ellipticals actually have subtle asymmetries and faint structures when observed carefully, echoes of ancient disturbances that have not yet completely relaxed. The galaxy looks peaceful, but if you know where to look, the scars of its violent past are still faintly visible. Not every elliptical is completely dead. Some contain small amounts of gas and dust, often acquired through minor mergers or cooling from the hot halo. In a few cases, This gas has settled into a small disk at the center, forming a structure called a kinematically distinct core, a disk of gas and young stars rotating within a galaxy that otherwise shows no ordered rotation. These cores are like small gardens planted in an abandoned building, surprising, incongruous, and quietly beautiful. They suggest that even the most quiescent galaxies can experience small episodes of renewal if new material arrives. Lenticular galaxies occupy an interesting middle ground. They have disk structures like spirals, but very little gas and no spiral arms. Their stellar populations are predominantly old and red. They are sometimes described as stripped spirals, galaxies that once had the full apparatus of a spiral galaxy, but lost their gas through one mechanism or another, causing star formation to cease while the disk structure remained intact. Lenticulars are common in galaxy clusters, where environmental processes can efficiently remove gas without destroying the disk itself. The transformation from spiral to lenticular may happen through several different routes. Ram pressure stripping in a cluster can remove the gas while leaving the stars and disk structure intact. Strangulation, the cutoff of fresh gas supply from the circumgalactic medium, can cause star formation to fade gradually as existing gas is consumed without replacement. Tidal interactions can heat the disk and suppress star formation. Each pathway produces a lenticular galaxy with slightly different properties, and disentangling which process was responsible for any individual galaxy is one of the ongoing challenges in the field. Let's step out now into the largest environments galaxies inhabit: the galaxy clusters. These are the metropolitan centers of the cosmic web, the nodes where filaments converge and thousands of galaxies gather within a single enormous dark matter halo. A large cluster can contain hundreds to thousands of galaxies, spanning 10 to 30 million light-years across, bound together by gravity and immersed in a sea of hot gas that fills the space between them. Moving into a galaxy cluster feels different from wandering through a group. The scale is overwhelming. Galaxies are everywhere. Ellipticals dominating the center, spirals more common toward the outskirts, lenticulars scattered throughout. The brightest cluster galaxy sits at the center like a monument, often an enormous CD galaxy with a diffuse envelope of stars stretching far into the surrounding space. Around it, galaxies orbit at speeds of 1,000 kilometers per second or more, their motions too fast for gravity to easily bind them into merging pairs. In a cluster, galaxies tend to fly past each other rather than sticking together. They are too fast for the gentle, prolonged interactions that characterize groups. But the cluster environment shapes galaxies in other ways. The hot intracluster medium, gas heated to tens of millions of degrees, glowing in X-rays, fills the space between galaxies. This gas is extraordinarily thin by terrestrial standards, far more tenuous than the best vacuum achievable in a laboratory. But spread across millions of light years, it adds up. The total mass of the intracluster gas in a large cluster exceeds the combined mass of all the stars in all the galaxies it contains. It is the dominant baryonic component, the most substantial reservoir of ordinary matter in these systems. When a galaxy falls into a cluster, it encounters this hot gas. And if the galaxy is moving fast enough, which in a cluster it usually is, the pressure of the intracluster medium pushes against the galaxy's own gas, stripping it away. This is ram pressure stripping at its most dramatic. The galaxy plows through the cluster atmosphere like a diver entering water, and its cold gas is peeled off and left trailing behind in a long, luminous wake. Some of the most beautiful examples of this are the jellyfish galaxies, spiral galaxies in the process of being stripped, their gas trailing behind them in long tentacles of material that stream away from the disk and stretch for tens or even hundreds of thousands of light years. Stars continue to form within these tentacles, creating blue knots of star formation that dangle behind the galaxy like glowing droplets. The galaxy itself is being robbed of its fuel, its star formation doomed to cease once the stripping is complete. But in the meantime, the tentacles create something hauntingly beautiful. A galaxy in the process of transformation, caught between what it was and what it will become. ESO 137-001, a spiral galaxy falling into the Norma cluster, is one of the most spectacular jellyfish galaxies known. Its gas tail extends for more than 200,000 light years behind it, longer than the galaxy itself, and within that tail, new stars are being born. Orphaned stars that will never be part of any galaxy, drifting freely through the cluster environment. The stripped gas eventually mixes with the hot intra-cluster medium, enriching it with metals processed through the galaxy's stars. In this way, the cluster environment is not just a destroyer of galaxies, it is a recycler, gathering material from many galaxies and redistributing it throughout the cluster volume. Ram pressure stripping is most effective for galaxies on radial orbits that plunge through the dense cluster core, where the intracluster medium is hottest and most pressurized. Galaxies on wider, more circular orbits experience weaker stripping and may retain their gas for longer. The orientation of the galaxy also matters. A galaxy moving edge-on through the cluster gas experiences less cross-sectional pressure than one moving face-on. These factors create a diversity of outcomes. Some galaxies are stripped quickly and completely. Others lose gas gradually over multiple orbits. Some lose only their outer gas, while retaining enough in the center to continue forming stars for a while longer. The cumulative effect of ram pressure stripping across many galaxies contributes to the morphology density relation, one of the most robust observations in extragalactic astronomy. In the dense cores of clusters, elliptical and lenticular galaxies dominate. In the sparse outskirts, spirals are more common. Moving from the edge to the center of a cluster, the fraction of spiral galaxies drops steadily, while the fraction of ellipticals and lenticulars rises. This gradient was first quantified by Alan Dressler in 1980 and has been confirmed in hundreds of clusters since. It tells us that environment matters. Galaxies in dense environments look different from galaxies in sparse ones, and the processes that operate in those environments are responsible for the difference. The morphology density relation holds at every scale, not just in clusters. Galaxy groups show it too. Even within the field, the low-density regions between clusters and groups, there are subtle correlations between a galaxy's properties and the density of its surroundings. The universe is not democratic in its treatment of galaxies. Where you live shapes what you become. Strangulation is a gentler version of environmental quenching. When a galaxy falls into a cluster or a group, its supply of fresh gas from the intergalactic medium is cut off. The galaxy can no longer replenish its disk with new fuel. It continues to form stars from its existing gas supply, but that supply is finite, and eventually it runs out. Star formation declines gradually, fading over a timescale of a few billion years as the gas is consumed without replacement. The galaxy transitions from blue to red, from star forming to quiescent, not through a dramatic stripping event, but through slow starvation. Strangulation and ram pressure stripping often work together. A galaxy entering a cluster may lose its outer gas to ram pressure relatively quickly, while the denser gas in its central regions persists for longer. Simultaneously, the cutoff of fresh inflow ensures that even this residual gas is eventually consumed. The two processes conspire to quench the galaxy on a timescale that depends on the galaxy's mass, its orbit through the cluster, and the density of the intracluster medium it encounters. Harassment is another environmental effect. The cumulative damage done by frequent, high-speed encounters with other galaxies in a cluster. No single flyby is dramatic enough to destroy a galaxy, but over billions of years, the gravitational jolts from many passing neighbors can heat the disk, thicken it, strip away loosely bound stars, and gradually transform a spiral into a more rounded, featureless system. Harassment is thought to be particularly important for low-mass galaxies, which are more vulnerable to gravitational disturbance. It may be one of the reasons why dwarf ellipticals are so common in clusters, while dwarf irregulars are more common in the field. The intracluster light, the diffuse glow of stars between galaxies in a cluster, is a direct consequence of all these environmental processes. As galaxies are tidally stripped, harassed, and disrupted, some of their stars are flung free, no longer bound to any individual galaxy. These orphaned stars drift through the cluster potential, orbiting the cluster's center of mass rather than any particular galaxy. In large clusters, the intracluster light can account for 10 to 40% of the total stellar luminosity. A substantial fraction of the cluster's stars belong to no galaxy at all. The intracluster light is faint and diffuse, making it difficult to observe. But deep imaging has revealed its presence in many clusters, sometimes showing streams, arcs, and other structures that trace the paths of disrupted galaxies. The intracluster light is, in a sense, the graveyard of galaxies, the scattered remains of systems that were torn apart by the cluster environment. Walking through it, you would be surrounded by stars that were once part of spiral arms, bulges, and dwarf galaxies, now drifting freely in a vast communal space, bound only to the cluster as a whole. The hot intracluster medium itself is a remarkable substance. Heated to temperatures of tens of millions of degrees by the gravitational energy released during cluster formation, it emits X-rays that can be detected by space-based observatories. The distribution of this gas traces the shape of the cluster's dark matter halo, and its temperature and density encode information about the cluster's mass and dynamical state. Clusters that have recently undergone mergers with other clusters show disturbed X-ray morphologies, asymmetries, cold fronts, and shock waves propagating through the gas. Relaxed clusters, those that have not been disturbed recently, show smooth, symmetric X-ray profiles centered on the brightest cluster galaxy. One of the most famous examples of a disturbed cluster is the bullet cluster, a system in which two clusters have recently passed through each other. The X-ray gas from the two clusters has collided and slowed down, creating a visible shock front. But the dark matter, which does not interact through any force other than gravity, has passed straight through, separating from the gas. Gravitational lensing measurements show the mass to be concentrated where the dark matter is, not where the gas is. This spatial separation between the dark matter and the baryonic gas is one of the most direct and compelling pieces of evidence for the existence of dark matter, and one of the most difficult observations for alternative theories like Mond to explain. The bullet cluster is a snapshot of a collision between two of the largest structures in the universe, and yet even it is a quiet affair by human standards. The collision unfolded over hundreds of millions of years. The shock front moves at thousands of kilometers per second, but across millions of light years, that speed amounts to a glacial pace. If you could witness it in real time, you would see nothing at all. Just a faint glow of X-rays in the dark, and two invisible mountains of dark matter sliding silently through each other. Galaxy clusters are still growing today. They continue to accrete galaxies from their surroundings, pulling in new members from the filaments of the cosmic web. This accretion is not steady. It often happens in bursts as groups of galaxies fall in together along a filament. These infalling groups bring their own processed galaxies, their own hot gas, and their own dark matter, adding to the cluster's mass and complexity. The cluster grows like a city, expanding its boundaries, absorbing neighboring towns, and transforming new arrivals as they adapt to the denser environment. The most massive clusters are also the rarest. They sit at the high end of the mass function, the distribution of structures by mass in the universe, and their abundance is exquisitely sensitive to the parameters of cosmology. Counting clusters and measuring their masses at different epochs provides one of the most powerful ways to constrain the properties of dark matter, dark energy, and the overall geometry of the universe. Clusters are not just environments, they are cosmological laboratories, each one a data point in our effort to understand the fundamental nature of the universe. Let's move now to the edges of clusters, where the transition between the cluster environment and the field occurs. This boundary is not sharp. Clusters grade smoothly into their surroundings, with the density of galaxies and hot gas declining gradually outward. But there is a region, sometimes called the splashback radius, where galaxies that have previously passed through the cluster are reaching the outermost points of their orbits before falling back in. Beyond this radius, galaxies are still on their initial infall, approaching the cluster for the first time. Galaxies in this infall region are already being affected by the cluster environment, even before they reach the denser central regions. They may be experiencing strangulation as their gas supply from the cosmic web is redirected by the cluster's gravitational influence. They may be part of infalling groups where pre-processing has already altered their properties. The transformation of a galaxy by its environment begins not at the cluster boundary but well beyond it, sometimes millions of light years away, in the filaments and groups that feed the cluster. This gradual environmental influence means that the life of a galaxy is not determined solely by its internal properties. Its mass, its gas content, its star formation rate. It is also shaped by its cosmic address. A galaxy born in a dense region, destined to fall into a cluster early, will have a very different life from one born in a void, far from any large structure. The universe is not a level playing field. Geography matters at every scale. And yet, amid all these environmental pressures, galaxies retain their individuality. Two galaxies of similar mass in similar environments can have very different star formation histories, different merger records, different chemical enrichment patterns. The scatter is real, and it reflects the complexity of galactic evolution. The fact that each galaxy's life is shaped by a unique combination of initial conditions, merger history, environment, and the stochastic nature of star formation and feedback. No two galaxies have had exactly the same life. Each one is, in its way, unique. Let's wander through one more environment before we move on. Some galaxies live in the quietest neighborhoods of all, the cosmic voids. These are the enormous, nearly empty regions between the filaments of the cosmic web, where the density of galaxies is far below average. Void galaxies are relatively isolated, experiencing few interactions and minimal environmental processing. They tend to be bluer and more gas-rich than galaxies in denser environments, still actively forming stars at ages when their cluster-dwelling counterparts have long since gone quiet. Void galaxies are interesting precisely because of what hasn't happened to them. They are the control group, galaxies that have evolved in relative isolation, free from the stripping, harassment, and merging that shape galaxies elsewhere. By comparing void galaxies to those in groups and clusters, astronomers can isolate the effects of environment from the effects of internal processes. The differences are illuminating. Void galaxies grow more slowly, retain their gas longer, and maintain their spiral structure for longer. They are the introverts of the galaxy population, quietly going about their business, while the social butterflies in clusters undergo repeated transformation. Even in voids, though, galaxies are not entirely alone. Small groups and pairs exist within voids, and interactions between them still occur, albeit less frequently. The cosmic web, even in its thinnest regions, still connects things. No galaxy is truly isolated. Everyone exists within a context, a web of gravitational relationships, gas flows, and dark matter structures that extends, ultimately, to the observable universe itself. The diversity of galactic environments, voids, filaments, groups, clusters, creates a diversity of galactic lives. A galaxy's life story is not just a function of its birth mass and initial spin. It is a function of every encounter it has had, every environment it has passed through, every companion it has absorbed or been stripped by. The life of a galaxy is an autobiography written in stars, gas, chemistry, and structure, and it can only be read by looking at all of these together, understanding how they connect, and appreciating that the galaxy we see today is the sum of everything that has happened to it across billions of years of cosmic time. As we stand here, somewhere in the middle of all of it, between the spirals and the ellipticals, between the clusters and the voids, between the quiet retirement of the old and the bright creation of the young, we can feel the diversity of the universe spreading outward in every direction. Each galaxy we pass is a world with its own history, and there are hundreds of billions of them, each one turning slowly in the dark, each one different, each one carrying the marks of a life lived across timescales we can barely imagine. We've wandered far tonight, through spiral arms and elliptical halls, through galaxy clusters and cosmic voids, through tidal streams and jellyfish tails and the quiet retirement of ancient giants. But there's one galaxy we haven't really explored yet, the one we're inside right now. Let's come home for a while. Let's walk through the Milky Way and look at it with fresh eyes, knowing what we now know about how galaxies live. The Milky Way is a barred spiral galaxy. It has a disk roughly 100,000 light-years across, a central bar perhaps 27,000 light-years long, and at least two major spiral arms with several smaller ones. It contains somewhere between 100 billion and 400 billion stars. The uncertainty itself is striking. The fact that we live inside something and still can't agree on how many stars it holds. Our sun sits in the disk, about 26,000 light-years from the center, in a region between two of the spiral arms. We are not at the center. We are not at the edge. We are somewhere in the quiet middle, orbiting at a comfortable distance, one star among hundreds of billions. From the inside, the galaxy is hard to see. We are embedded within the disk, and the dust that threads through the spiral arms blocks our view in many directions, especially toward the center. For centuries, we didn't even know we were inside a galaxy. It took radio astronomy and infrared observations to pierce the dust and begin mapping the structure we inhabit. Even now, our picture of the Milky Way's shape comes partly from direct observation and partly from inference, comparing what we can see with what we know about other galaxies of similar type. We know our home better than we used to, but we are still learning its layout, still discovering rooms we didn't know existed. The Milky Way's disk is not a single uniform structure. It has two components, a thin disk and a thick disk. The thin disk is where most of the current star formation happens. It is relatively narrow, extending only about 1,000 light-years above and below the midplane, and it contains the youngest, most metal-rich stars, as well as most of the gas and dust. The thick disk is older and puffier, extending 2,000 to 3,000 light-years above and below the midplane. Its stars are older, less metal-rich, and orbit with slightly more random motion. The thick disk is thought to be a relic of an earlier, more turbulent era in the Milky Way's history, a time when the disk was hotter and more disturbed, possibly puffed up by the energy of intense star formation or by an ancient merger. That ancient merger may be the Gaia Enceladus event we touched on earlier, a collision with a substantial galaxy roughly 10 billion years ago that deposited a large population of foreign stars into the halo and may have heated and thickened the pre-existing disk. If so, the thick disk we see today is partly a scar from that encounter, a layer of the galaxy that remembers a time of disturbance. Walking through the thick disk, we are walking through the archaeology of a collision that happened when the universe was less than 4 billion years old. The stars around us are old, and some of them were born in a galaxy that no longer exists. Above and below the disk lies the stellar halo, a vast, roughly spherical cloud of old stars, globular clusters, and tidal streams that extends for hundreds of thousands of light years. The halo is faint, containing only about 1% of the galaxy's total stellar mass, but it is enormously important as a record of the Milky Way's accretion history. Many of its stars were not born here. They came from other galaxies, dwarfs and satellites that were captured and torn apart over billions of years, their stars scattered throughout the halo like the belongings of travelers absorbed into a city. The globular clusters of the halo are among the oldest objects in the galaxy. These dense, spherical collections of hundreds of thousands to millions of stars formed very early in cosmic history, many of them more than 12 billion years ago. Some were born within the Milky Way itself. Others were brought in by accreted galaxies, their original homes long since dissolved. The chemical compositions and orbital properties of individual globular clusters can reveal which ones are native and which are immigrants. The Milky Way's halo is a museum of ancient arrivals, each globular cluster a display case from a different era and a different origin. Omega Centauri, the most massive globular cluster in the Milky Way, is believed by many astronomers to be the stripped core of an ancient dwarf galaxy. It contains roughly 10 million stars and shows evidence of multiple generations of star formation, unusual for a globular cluster, which typically forms all its stars in a single burst. If Omega Centauri is indeed the remnant of a galaxy, then it is the heart of a world that was consumed, still beating faintly within the body of the galaxy that absorbed it. There's something haunting about that. A galaxy reduced to its core, orbiting quietly within the halo of its captor, carrying the last trace of an identity that was otherwise erased. At the very center of the Milky Way sits Sagittarius, a star, the supermassive black hole with a mass of roughly 4 million suns. We explored supermassive black holes earlier tonight, but let's pause here for a moment and consider what it means that this particular one is ours. It sits at the gravitational heart of everything we see when we look up at the night sky. Every star you've ever seen with your naked eyes is orbiting around it. Every constellation, every familiar pattern, is part of a vast, slow spiral centered on this point. And at that point, there is something so dense and so extreme that space and time themselves are warped beyond recognition. The region immediately around Sagittarius, the star, is extraordinary. A dense cluster of stars orbits within just a few light years of the black hole, moving at speeds of thousands of kilometers per second. The star, called S2, has been tracked completing a full orbit in just 16 years, swinging within 120 astronomical units of the black hole, about 3 times the distance from the Sun to Pluto. At its closest approach, S2 reaches speeds of nearly 3% of the speed of light. Watching these stars is like watching planets orbit a sun, but compressed into an environment of unimaginable gravity and energy. Despite its enormous mass, Sagittarius A star is quiet. It accretes very little material at the moment and produces relatively little radiation. Compared to the blazing quasars of the distant universe, our black hole is dormant, a sleeping giant at the center of an otherwise active galaxy. But as we noted earlier, it may not always have been this way. The Fermi bubbles, enormous lobes of hot gas extending 50,000 light-years above and below the galactic plane, may be the remnants of a more active past, a time when Sagittarius A star consumed more gas and belched energy outward into the halo. Our galaxy's heart has known both silence and thunder. The Milky Way is still forming stars today, though at a modest rate. The current star formation rate is roughly 1 to 2 solar masses per year, concentrated in molecular clouds scattered throughout the disk, particularly in the spiral arms. The Orion Nebula, one of the closest and most famous stellar nurseries, is producing new stars right now, about 1,300 light-years from Earth. The Carina Nebula, much more distant and much more massive, is another active region, home to some of the most luminous and massive stars in the galaxy. These nurseries are the galaxy's workshops, the places where its story is still being written. The Milky Way's gas supply is not infinite. The galaxy continues to receive some fresh material from the cosmic web and from its satellite galaxies, but the rate of inflow is thought to be lower than the rate at which gas is being consumed by star formation. Unless something changes, a new accretion event, a major merger, the Milky Way's star formation will gradually decline over the coming billions of years. The galaxy is not dying, but it is aging. The peak of its star-forming life is behind it, and the future holds a slow, gentle fade. The Milky Way's immediate neighborhood is the local group, a collection of about 80 galaxies spread across roughly 10 million light-years. The two dominant members are the Milky Way and the Andromeda Galaxy, also known as Messier 31. Andromeda is the nearest large galaxy to our own, about 2.5 million light-years away, and it is a spiral of similar size, perhaps slightly larger and more massive than the Milky Way, though the exact comparison is still debated. It has its own set of satellite galaxies, its own supermassive black hole, its own complex history of mergers and accretion. If the Milky Way is our home, Andromeda is the house across the road, close enough to see clearly, similar enough to compare, and heading directly toward us. The Milky Way and Andromeda are approaching each other at roughly 110 kilometers per second. This has been known for over a century. The blue shift of Andromeda's light was one of the first radial velocity measurements in extragalactic astronomy. What was not known until more recently was whether the approach was head-on or a near miss. Precise measurements from the Hubble Space Telescope, published in 2012, showed that the two galaxies are on a nearly direct collision course. In about 4 to 5 billion years, they will have their first close encounter. Let's imagine that encounter. Picture the sky 5 billion years from now. Andromeda, currently a faint smudge, visible on clear nights, has been growing slowly larger for billions of years. As the two galaxies approach, Andromeda fills more and more of the sky, a vast spiral of light, its arms and dust lanes becoming individually visible. At some point, the night sky transforms. Instead of a single band of light from the Milky Way, there are two, intersecting, overlapping, merging into a complex tangle of starlight and dust. The first close passage would be dramatic to watch, though not in the way a collision sounds. Remember, stars almost never collide. The galaxies would pass through each other, their stars sailing past in vast, interpenetrating streams. But the gravitational disturbance would be enormous. Tidal tails would be flung outward, stretching hundreds of thousands of light years into the surrounding darkness. The disks of both galaxies would be warped and distorted. Gas would be compressed, triggering bursts of star formation. The sky would light up with new stars, new nebulae, new clusters born from the violence of the encounter. After the first passage, the two galaxies would swing apart, slow down, and fall back toward each other again. This dance would repeat. 2 passes, 3, each one bringing the galaxies closer, each one further scrambling their structures. The supermassive black holes at their centers would sink toward the merged system's gravitational center through dynamical friction, eventually forming a binary and spiraling together into a final coalescence, releasing gravitational waves that would ripple outward at the speed of light. The end result, a few billion years after the first encounter, would be a single, larger galaxy. An elliptical, most likely, its disk structure destroyed, its stars orbiting on random paths through a smooth, rounded system. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda. It will be a quiet place. Most of the gas will have been consumed in the merger-driven starburst or expelled by feedback. Star formation will slow to a trickle and eventually cease. The stars that remain will age, cool, and redden over the ensuing billions of years. Milkomeda will join the ranks of the elliptical galaxies, the retired elders of the cosmos, glowing softly in the dark. Our sun will not be around to see it. In about 5 billion years, roughly the same time scale as the Andromeda merger, the sun will exhaust the hydrogen fuel in its core, swell into a red giant, and eventually shed its outer layers, leaving behind a white dwarf. The timing is a coincidence, but a poetic one. Our star and our galaxy will both undergo fundamental transformations at roughly the same epoch. The sun will die quietly. The galaxy will be reborn in a new form. If we could somehow linger far beyond the Andromeda merger, billions and billions of years into the future, we would see the universe change in ways that are difficult to imagine but possible to outline. The expansion of the universe is accelerating, driven by dark energy, and this acceleration has consequences that unfold over enormous timescales. Today, we can see galaxies billions of light years away. The light from those galaxies has been traveling for billions of years to reach us, and during that time, the space between us and them has been expanding. But because the expansion is accelerating, the rate at which distant galaxies are receding from us is increasing. At some point in the distant future, many tens of billions of years from now, the most distant galaxies will be receding faster than the speed of light. Not because they are moving through space that fast, but because the space between us is growing at an ever-increasing rate. Their light will no longer be able to reach us. One by one, distant galaxies will fade from view, slipping beyond the cosmic horizon and disappearing forever. This process is already happening. Galaxies at the very edge of the observable universe are already receding at speeds close to or exceeding the speed of light, their light stretched to the farthest reaches of the electromagnetic spectrum. In the far future, the process will continue, and the observable universe will shrink. Not because galaxies are being destroyed, but because the light from them can no longer bridge the growing gap. Eventually, the only galaxies visible from Milkomeda will be those in the local group, the ones bound together by gravity, tightly enough to resist the expansion. The rest of the universe will have vanished beyond the horizon. An observer in Milkomeda, looking outward, would see only darkness. No distant galaxies, no filaments of the cosmic web, No evidence that the universe contains anything beyond their own gravitational island. They would live unknowingly in a shrinking world. This is one of the strangest consequences of the accelerating expansion. The universe isn't just getting bigger, it is getting lonelier. The cosmic web, which connects everything today, will eventually be pulled apart. Each gravitationally bound group will become an island, isolated in an ocean of expanding space, with no way to know what lies beyond. Within Milkomeda, the story continues on smaller timescales. Star formation will have long since ceased, the gas supply exhausted. The existing stars will continue burning for as long as their fuel lasts. Massive stars, which burn hot and fast, will have died long ago, within a few 100 million years of their formation. Sun-like stars will persist for roughly 10 billion years, but the smallest, coolest stars, the red dwarfs, which make up the vast majority of all stars, will burn for trillions of years. Long after the last sun-like star has faded, the red dwarfs will still be shining, dim and steady, sustaining the galaxy with their faint, enduring light. Red dwarfs are the patient ones. A typical red dwarf has a mass of about 10 to 50% of the sun's, and it burns its hydrogen fuel so slowly that its lifetime stretches to tens of trillions of years, far longer than the current age of the universe. In the far future, the galaxy will be a sea of these small, cool, red stars, their light barely enough to illuminate the space around them. The galaxy will glow, but dimly. It will be warm, but just barely. The grand, luminous era, the age of blue giants and spiral arms and bursts of creation, will be a distant memory encoded in the cold remnants of dead stars. As the red dwarfs eventually exhaust their fuel, they too will fade. They will contract into white dwarfs, dense, Earth-sized remnants that cool slowly over billions of years, radiating away the last of their thermal energy. The galaxy will transition from a collection of living stars to a collection of cooling embers. White dwarfs, neutron stars, and black holes, the remnants of all the stars that ever lived, will drift through the galaxy in the dark, their orbits unchanged, their gravity still holding them in the system, but their light gone. This era, sometimes called the degenerate era, will last for an almost incomprehensible length of time. White dwarfs cool so slowly that it takes hundreds of billions of years for them to fade significantly and trillions more to cool to near absolute zero. The galaxy will not suddenly go dark. It will fade imperceptibly over timescales that make the current age of the universe look like a camera flash. Occasionally, over these vast timescales, something dramatic will happen. Two white dwarfs in a binary system may spiral together and merge, producing a brief flash of light, a Type 1a supernova, flaring in the darkness like a single match struck in an enormous empty room. These events will become increasingly rare as the supply of suitable binary systems dwindles, but for a long time, they will be the only sources of new light in the galaxy. Each one a reminder that the universe, even in its old age, is still capable of surprise. Neutron stars, the ultra-dense remnants of massive stars, will also persist. They spin, they cool, they gradually slow down. Some will continue to emit faint radiation for billions of years. Others will collide in rare, spectacular events, neutron star mergers that produce bursts of gravitational waves, flashes of gamma rays, and sprays of heavy elements. These events, vanishingly rare, will be among the last energetic phenomena in the galaxy's long twilight. Black holes will be the last survivors. Stellar mass black holes, scattered throughout the galaxy, will drift on their orbits indefinitely, interacting with nothing, absorbing nothing, simply existing. The supermassive black hole at the center of Milkomeda, the merged remnant of Sagittarius' star and Andromeda's black hole, will sit at the heart of a galaxy that has gone dark around it. Occasionally, over immense timescales, a stray object will wander too close and be consumed, producing a brief flicker of accretion. But these events will become rarer and rarer as the galaxy empties. Even black holes, though, are not eternal. Stephen Hawking predicted that black holes slowly radiate energy through a quantum mechanical process now known as Hawking radiation. The rate of this radiation is extraordinarily small for large black holes. A supermassive black hole would take something like 10 to the power of 100 years to fully evaporate. That number is so vast that writing it out would require more zeros than there are atoms in the observable universe. But it is finite. Given enough time, even the black holes will vanish, dissolving into faint wisps of radiation and leaving nothing behind. After the black holes evaporate, in an era so distant that all previous cosmic history occupies a negligible fraction of the elapsed time, what remains is difficult to describe. A thin scattering of elementary particles, the remnants of Hawking radiation, spread across a universe that has expanded to incomprehensible size. No structures, no light, no heat. The temperature of the universe asymptotically approaches absolute zero. This is the heat death, the final equilibrium from which no further change is possible. It sounds bleak when described in words, but let's step back from the far future and return to the present for a moment, or rather, to the perspective we've carried with us tonight. Because the story of galaxies is not a story about endings. It is a story about time and patience and the extraordinary things that matter does when given enough of both. We have walked tonight through structures that span 100,000 light years. We have watched spirals turn, ellipticals glow, clusters churn, and voids hold their silence. We have followed gas as it cycled through generations of stars, enriching itself with heavier elements at each turn. We have watched galaxies consume their companions and reshape themselves through mergers that last billions of years. We have stood in tidal streams made of stars from galaxies that no longer exist, and we have peered into the far future where the universe grows dark and quiet and the last black holes dissolve into nothing. Every galaxy we've explored tonight has a story that stretches from the earliest moments of cosmic time to an ending we can barely conceive. And within each one, for a brief window, a few billion years out of trillions, conditions are right for something astonishing. Stars burn at the right temperature. Planets form from the right chemistry. Atmospheres hold the right gases. And in at least one case, on at least one small world, orbiting an unremarkable star in the quiet middle of a spiral galaxy, matter organized itself into something that could look up and wonder about all of this. That is where we are right now. Inside the story. Not at the beginning, not at the end, but somewhere in the vast, luminous middle. The era when galaxies are still bright, still forming stars, still connected by the filaments of the cosmic web, still close enough to see each other across the expanding dark. This is the age of light. It will not last forever, but it is here now, and we are part of it. The iron in your blood was forged in a star that lived and died before the sun was born. The calcium in your bones was scattered by a supernova billions of years ago, drifting through the interstellar medium until it was swept up into the cloud that collapsed to form our solar system. The hydrogen in every glass of water you've ever drunk has been in the galaxy since the beginning. Since before there were stars, since the first gas clouds condensed from the cooling aftermath of the Big Bang. You are not separate from the galaxy. You are made of it. You are the galaxy, rearranged into a form that can lie quietly in the dark and think about where it came from. Tonight, as you rest, the Milky Way is turning. The spiral arms are winding through their slow compression waves, triggering the birth of stars you will never see. Gas is cycling through the circumgalactic medium, rising and falling in a fountain that has been running for billions of years. Dwarf galaxies are being slowly torn apart in the halo, their stars joining a population of immigrants that will never know where they came from. And at the center, Sagittarius A star sits in its patient silence, surrounded by stars that orbit so close to it they move at a fraction of the speed of light. All of it is happening right now. All of it has been happening for 13 billion years. And all of it will continue in one form or another for timescales so long that the human mind can hold them only as abstractions. But you don't need to hold them. You don't need to grasp any of it tonight. It is enough to know that it is there, that the galaxy is alive with slow, vast, quiet processes that connect you to everything that has ever been and everything that will ever be. 2.5 million light years away, Andromeda is drifting closer. In 5 billion years, the sky will change. The two galaxies will meet, dance, and merge into something new. And whatever exists in that new galaxy, whatever stars burn, whatever worlds form, whatever minds look up at whatever sky, they will be the inheritors of everything we explored tonight. Every spiral arm we wandered through, every elliptical hall we stood in, every tidal stream we traced, all of it will be woven into the fabric of whatever comes next. But that is a long way off. Tonight, the galaxy is as it is, bright, complex, alive, and you are resting within it, one warm presence in a spiral arm, drifting gently towards sleep while the stars turn overhead. If you happen to still be awake, you can go ahead and watch the next video now. Another quiet journey will be waiting for you, another set of rooms to explore, another chance to wander through something vast and hidden and full of wonder. But if your eyes are heavy and your thoughts are dissolving into the soft static of approaching sleep, then let them go. The galaxies don't need you to stay awake for them. They have been doing this for a very long time. They'll still be here in the morning, turning, glowing, breathing their slow breath of gas and starlight. Thank you for coming along tonight. It's been good having you here. Sleep well, dream of slow spirals and ancient light. Good night.